Example 2, we've got P given by 2AP AP squared, Q 2AQ AQ squared are 2 points on the parabola x squared equals to 4ay. And part 1, we want to show that the equation of the chord PQ is given by y is equal to half P plus QX minus APQ. Now I'm just going to be skipping out on this because I have shown you guys how to derive, right, the standard equation of the chord PQ a number of times already. So you guys can check this out either in example 1, right, or in the beginning theory introduction where I proved the parametric equation of the chord PQ generically. Okay, so I would just be skipping out on this, but you guys need to know, okay, how to prove this. That's important, right? So I'm skipping this because I have done this a number of times already. And I'm assuming that you guys want me to skip this also because it's quite repetitive. Okay, but if you guys don't know how to do this, make sure you guys check up on the previous parts. So now jumping to the main part of the question, okay, it tells us that given Q is equals to 3, for what values of P will this chord also be a normal to the curve at P? Now to start, let's say we get a parabola out. Okay, so that's going to be the x-axis and this is going to be the y-axis. Just doing this roughly, okay, but this is origin, x and y, right? And now for the parabola, let's say we've got a parabola which looks roughly like this. Oh, that's pretty good. Okay, beautiful parabola. So that's x squared equals to 4ay. So I've got 2 random points on the parabola, except when they tell us that Q is equals to 3, that fixes the point Q. Okay, so it's fixed now. It's no longer variable. So the point Q that we're dealing with is 2a times 3, a times 3 squared. So in other words, 6a, 9a. Okay, so let's say Q is fixed over here. Okay, so this is going to be 6a, 9a, and it's of course corresponding to the parameter small q is equals to 3. Okay, you guys need to take note that when we fix the parameter q to be equals to some value, then my point q is no longer just any point on the parabola, but it's a fixed point. Okay, it can no longer move. Now, if that's the case, we've still got the point P to AP squared, right? And we know that P can be anywhere it wants to be. And no matter where P is, the moment I join from P to Q, that's going to be the chord PQ. Now, what I want to do is I want to find values of P for which the chord PQ is also going to be a normal to the curve at the point P. Now, we know that we can draw infinitely many points for P, right? P can be wherever it wants to be, but some of those points, okay, is going to be a normal because at those points, if I draw a tangent, okay, if I draw a tangent at P and somehow the chord PQ is perpendicular to the tangent at P, then in those situations, I can say that the chord PQ is also a normal to the curve at P. Okay, so what we need to recognize is that chord PQ, okay, chord PQ is also a normal to the curve at P, right? If it is perpendicular, okay, out of space, perpendicular to the tangent at P. Okay, so this is a pretty good start. So how am I going to find the values of P, small p, such that the chord PQ is also going to be a normal? This is how I'm going to start. So this tells us what we have to do in order to find the values of P. Okay, so to start, we know that the equation of the chord is given by half P plus Q times X minus APQ. Of course, if we know that Q is equals to 3, then this equation becomes Y is equals to half P plus 3 times X minus A times P times 3, which is minus 3AP. So this is going to be the chord PQ if Q is equals to 3, okay? And we can see that the gradient of this chord right now is half P plus 3. Now, on the other hand, at the point P to AP squared, right, if I differentiate for dy dx, okay, so dy dx is going to be dy dp over dx dp, that's going to give us 2AP over 2A, right? Differentiate AP squared with respect to P, you get 2AP. Differentiate 2AP with respect to P, you get 2A, right? The 2A's cancel out, and this is going to give you P. And what this represents is the gradient of the tangent. So I know the gradient of the tangent at the point P, and I've also got the gradient of the chord PQ. So I said earlier when we were setting up the question that the chord PQ is going to be a normal, right, at P if the chord PQ is perpendicular to the tangent at P. So if the chord PQ is perpendicular to the tangent at P, then the product between the gradient of the chord and the gradient of the tangent needs to give us -1. Okay, so if chord PQ is also normal, okay, then what we're saying is that the gradient of PQ times the gradient of the tangent needs to give us -1. Okay, in other words, this is going to be exactly equals to the gradient of the normal at P. But anyways, that being said, let's check out the algebra. The gradient of the tangent is P. The gradient of the chord is half P plus 3. So if I multiply half P plus 3 with P, then that's going to give us -1. If I multiply 2 to the right and I expand the bracket, we're looking at P squared plus 3P is equals to -2. Or in other words, if we rearrange, we're now looking at P squared plus 3P plus 2 is equals to 0. And we can solve this very easily, right? First, it factorizes into P plus 1 times P plus 2 is equals to 0. And then it tells us that P is equals to -1 or P is equals to -2. So if P is equals to -1, okay, that's going to be corresponding to like a point over here. My diagram is a little bit off, okay, for which the point P, okay, is going to be fixed. Of course, P is given by 2AP squared. So it's telling us that small p equals to -1 is going to give us a point on the parabola such that the chord PQ is going to be perpendicular to the tangent at P at that particular point. And it's going to happen again at the point P that corresponds to the parameter small p equals to -2. So this is essentially the solution, right? Because we found the values of P for which the chord is also going to be a normal to the curve as well. Okay, so this concludes example 2.